Okay, we're getting to bases for subspaces. So this notion of bases will be very, very important. But to start with, we're going to work through an example, a new one. So this is, here we are. It's going to be a new friend. We're going to call Inigo here for some reason. And it's this 2 by 3 matrix. So just like Physic, we'll have really a long analysis later on, but we have to put all these pieces together. There will also be the man in black. So there are going to be these 3 matrices that we'll work through. But you can see 1, 2, 2, 4, 1, 2. So you can see the rows are multiples of each other, and so are the columns. So it has a lot of redundancy, which is good for us in our quest to understand what's going on with these subspaces. So very exciting, I know. This is I don't know about the care and feeding. That may be here. We'll see if that emerges. It's a bonus. I try to have the cat here, but the cat keeps leaving. Spanning sets. We'll get to that just at the end of this piece. Bases are in the next piece, and how all this connects with dimensions of subspaces. Very good. All right, so let's work through things. I've set out a lot of this. There's some boring but important stuff about whether a set of vectors is a subspace or not, and we'll get to that. Okay, so simple thing to start with. We're just going to find the column space and the null space, talk about them a little bit. The next piece, we'll talk about bases in general and spanning sets, and then we'll come back and analyze this new friend of ours with some extra things in our head. So there should be 3 pieces here in a row. All right, so we will have 3 ways of finding column space. We have 1 so far, so let's just go with that. Okay, so it is that we set up with an arbitrary B1 and B2 because we're trying to find which values of B1 and B2, which vectors B can we actually make. And if you look at this matrix, you can see that we can only make multiples of 1, 2. But let's go through the procedure. It's always good. It's always healthy for us to do that. So we're solving, again, the augmented matrix story with an arbitrary B. Row operations, just do what we've always done. Yes? So in blue are the standard structures. We're changing row 2. The new row 2 is all zeros. That's what we're trying to get to. But we're at least trying to put a 0 here. And to do that, we have 2 divided by 1, 2 divided by 1, right? So the first pivot is there, and it turns out to be the only pivot in this case. So let me annotate that one. So this is D1. So we use that, and here it is on the bottom. This is our first multiplier. L21, that's in brackets. Usual stuff, just to say it'll show that all connects. All right, so once we do that one set of one instance row operations, in fact, we get a row of zeros, and instead of B2, we now have B2 minus 2B1, right? We're subtracting 2 of the first row away. So that's it, we're done. There's 1 pivot, so let's mark those things, that's important. I'll use red again. Pivot, free, free. So over here we'll say that we'll note a few things. So the dimensions are m equals 2, 2 rows, n equals 3, 3 columns. So rows, columns, I'm happy to repeat these things, always the same. And then r equals 1, the rank. This is a rank 1 matrix, which really means it's just a number. It will take 1 line in 3 dimensions and send it to a line in 2 dimensions, and it will stretch or shrink that line. Okay. We'll see this matrix is really just a number of sorts. What that number is will take a while, but it takes a line somewhere, as I said, in 3 dimensions, going through the origin, takes it over to a 2-dimensional space and remaps it, and everything else in this 3-dimensional space gets sent to 0. I mean, everything that's orthogonal to that line, I should say. All right, we'll get to that. Okay, so column space. Let's find column space first. We've set this up. This has to be 0 for column space, for a vector to be in column space. Otherwise, we'll have 0 equals a non-zero number. And that does not work. Can't do it. All right, so b2 minus 2b1 equals 0. Again, this is one way of the three ways. It doesn't generalize very well, but we're fine with it here. So we can rewrite this so that b2 equals 2b1. That's this piece here. Fine. So think of this as, let me mark this, so we'll make this dependent, right? Dependent and independent. For the null space, we think of free and pivot, right? That's clearer there. Only one way to do it. Repeat, repeat, repeat. All right, so this piece is left undone. So we're going to replace the dependent one by what's by what it is in terms of the independent. So that's right. This piece goes to here. B1 stays the same. It's independent. So now we're at. I can pull a B1 out, which we do with alacrity, and so it's any multiple of 1, 2. So let's say column space equals the set of all vectors x. You know, it's a difference. I'll do the right thing. It's really, we're going to call those ones y in general. It's in 2 dimensions, such that y equals some multiple. I'll just put a c times 1, 2, where c is an element of the real numbers. Clearly a subspace. By the way, when you think about it, it's a line through the origin. Right, line through origin. But we'll say something a little more general about why this is a subspace. Just a little bit more about it in a second. Okay, so this makes sense. And again, this is very important. These curly brackets matter, right? This means it's a big set of things. This means this is conditional, right? So all vectors in R2, provided they have this structure. Great, so we've got it. It's one-dimensional, right? Which matches up with rank 1, which we're getting to in a little bit. All right, let me actually write that. So this is, things escaping on me. So this is 1D, a 1D subspace of R2. And this, let's annotate that one. So R equals 1 is that one, and 2, this is M equals 2. That's where that comes from. All right, good. Good. Okay, everything's there. Zoom over here. So null space. Let's work on null space. So we're solving that AX equals 0 problem, right? The homogeneous problem. Because we figured out that if we solve this problem, whatever we get for it, we can always add to any specific or particular solution. That's the technical term. We'll see that they are, in fact, vectors in row space. Okay. Yeah. Yeah. All right. Yeah. Okay. All right. The monks over there, they're actually just Pokemon Go. It's strange, actually. Yeah, they're kind of into that. All right. So they seem happy. All right. So let's see. So 1, 2, 1, 0. We've got this set up, right? We just go back over here, set these b's to 0, which always ends up with zeros here. Doesn't matter what row operations do to them. So it's already done. And of course, this is really, if I can write this here, this is really the reduced row echelon form, which you're becoming very friendly with, and 0. Right, back over here, this is the reduced row echelon form. And because it's more general, it's D. Okay. Good times. All right, so we are going to take this first row here. That's the only one that has information. Just write it out. Write out the equations. Matches here. Right, so it's 1 times x1, 2 times x2, 1 times x3 equals 0. And let's write out which ones are the pivots. So again, pivot, free. So pivot variable, free variable, free variable. So we put the pivots in terms of the 3. Always do this. Right? Pivots, we express in terms of the 3. Just great. Everything is coming together very nicely, isn't it? It's a lot, I know. Just got to keep building and building and building. All right. Okay, so that's, I'm going to move this a little bit. All right, so now we always do this. Always. Right? X1, X2, X3, whatever you need to do. Just write them down. And then we replace, I'm going to add express pivots in terms of the free, pivot variables, I should say, I guess. So pivot variables in terms of free variables to be completely clear. I know, clarity, right? And so we're going to replace, now we'll do it over here. We'll replace pivot variables. They are just like the dependent variables. We've seen that they only appear once. So x1 is now minus 2x2. I shouldn't have all this red. Extreme. The free variables do not change. They're here. The pivot gets replaced with the free. This is good. Nutritious. And now we can spread it apart, right? So this is something you should be doing over and over again. x2, let's look at what's there. It has a minus 2 times x2 here, and then there's a 1, and then a 0, and then plus x3, I'll come back to it, minus 1, plus 1 here, and a 0 here. And then you'd say where x2 and x3 are elements of the real numbers. Let me just finish this off. So the null space of A is equal to all x in R3, and this is n equals 3, such that they have to equal this, some combination of these things. So let's just call them C1, doesn't really matter, minus 2, 1, 0. This is not the only way to express it, and that's going to be our next realization. As they come crushing in, the realizations, C1 and C2 are elements of the real numbers. Close curly brackets. All right. So let's go back and look at what we've just done. All right, so we put in the pivot variable in terms of the free, and then saw which, so we pull out the x2 and the x3, and then we take out the pieces that are multiplying them, right? So x2 only appears here and here, so we're going to get a minus 2 and a 1. And x3 only appears here and here. There's really implicitly a 0 x3 here. So minus 1, 0, 1. Minus 1, 0, 1. And then this is writing it out in full, right? So this last piece here is this is the expression of the actual, let's think I'm neurotic. So this is the actual set, right? If we want to say, well, let me say it like this. Very compactly, we can just say, look, here are two vectors. Take every linear combination of them, you get null space. So we could just hand someone those two vectors. That's very small. It's a little box. This one is the whole thing. We hand the whole thing. It's a line or a plane. In this case, it's a plane in 3 dimensions. So let me write that down. This is a plane in 3D, or R3. All right? And it's always true in general that the column space of A is a subspace of, I'll argue on the next page that that's true, of Rm. Right? A is m by n. M is the number of rows. N is the number of columns, and that's where null space lives. Right? So where the x's are, and the b's live over here. Right? Is a subspace of. Good. All right. So this is boring but important. I'll just go through it quickly. So here's the question. How do we know that these column spaces are really subspaces and not just some crazy town banana pants subsets? Well, basically the story is that because they're all linear combinations of whatever vectors, and for general null spaces and general column spaces, here's the particular example. Because they're all linear combinations, that really means they're automatically subspaces. So let's just go through how that works here. There are three properties that have to be satisfied for a set to be a subspace. If we've got two vectors in that subspace, then we add them together, right? So if we add them together, they're still in the subspace. So let's just make up two, right? So they have to be some multiple of the first vector plus some multiple of the second one. I've changed these things. So we've got x1 and x2 with different subscripts here. Add them together and we get C1, 1, this is right, so that these two add together because they're multiplying the -2, 1, 0 and the -2, 1, 0. And these two add together, yeah? So it clearly works, right? These are still constants, right? Some constant times the first vector, some constant times the second vector. So still a vector in the null space of A. The second property is if you multiply a vector by some scalar, still true, some constant that's in the real numbers. Let's take it, right? So let's say this is x1 times c, right? x1 times c. So we're just multiplying the first number and the second number. Fine. This is still a vector inside the null space because the null space is all linear combinations of these two vectors. Great. And then the last one in this boring set of things is that 0 is in the null space clearly, right? So we can take 0 of the first vector and 0, right? Multiply them by 0, add them together, we get all zeros. So yes. So it is a subspace. And the general story is this, is that sets made up of, right, so this piece here, sets made up of all linear combinations of some set of vectors are automatically subspace of wherever those vectors live. Because they will satisfy these three exciting rules of subspaces. And so this is just leading into the next piece. We'll start to use these words, we'll say that these two vectors, in particular this is for null space, span the null space of A, right? So these two vectors span the null space of A. That means that if you take all linear combinations, you'll get the null space. And then we'll say that these two vectors in a little box, right? You hand them over, here's one vector and another vector, very simple things, just two little arrows if you like, just hand them over. Sets of three numbers here, true. Are a spanning set for the null space of A. That's a much simpler encoding, right? Just like I hat and J hat, that's a spanning set for 2 dimensions, and it's they're very nice because they have length 1. That's going to be a big deal. They're at right angles to each other, so we kind of like those sort of bases, and we'll get to seeing how we can make those things happen, and also where they come out for free, which is just what a joy, what a joy. So that's in the next piece, and then if you've got a minimal spanning set in that if you take one of them away, you can't reach the whole of your subspace, then you have a basis, just like I hat and J hat are for 2 dimensions. If you take one of those away, right, you can't get there. So that's next, but this is just a start. So we've set up Inigo, and now we know nullspace, right? The subspaces are always the linear combinations of vectors are all linear combinations of vectors are always subspaces. So we're starting to get somewhere. The spanning sets will go to bases, and that will give us dimensions.